everyone. Welcome to another episode of Corecast. I'm your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Queercast. Before we get to it, if you haven't already, do join our Discord channel so you can ask us questions there. And if you're watching on YouTube, do ask us questions so we can get to them during the episode. Also, for those of you that don't watch this live, we do this every week, Tuesday at 5 p.m. So join us if you can. Now, without further ado, I guess Tim, I was wondering about randomness in some sense. Like when you say, "Oh," when I bump into somebody, I'm like, "Oh, that was so random." And I was thinking, like, what? Where does that come from? Is that is that from probability? Like, what do you think?
Yeah, I think loosely talking about randomness, I think when we say randomness, we mostly mean uncertainty. It's just the lack of ability to predict something. And from that respect, then many things in the world are random just because we cannot predict. But of course, most of these, lack of predictability, we can argue that it's down to our ignorance, just because we don't have enough information, right? So like I bump into you, it's just because I wasn't anticipating that, but maybe we're gonna bump into each other anyway, right? So so from that respect, a lot of uncertainty in our everyday lives are not really random, right? They're just a lack of information.
Huh. So, are you supporting a deterministic view of the world, and that we just don't know enough? And if we knew enough, would there be no randomness?
I can tell you the way that like a typical physicist would answer this. A typical physicist would say that there's like two kinds of uncertainty. There is the kind of uncertainty that we're familiar with in casinos, where you roll the dice and it's random but probabilistic. But as we all know, if we really knew the exact trajectory and the exact positions and velocities of every single atom in the dice, it would be deterministic. And then the typical physicist will say that we should not confuse this kind of randomness with the fundamental kind of randomness that comes from quantum mechanics. And they'll typically say that quantum mechanics is this theory that has a very mysterious kind of randomness in it. And we shouldn't try to think too hard about where that comes from, and we'll just get ourselves confused. But there is a way to make sense of that fundamental randomness too. And so I think that's what we're hoping to get into.
I see. So, can we just boil it down to like quantum mechanics is random, thus the world is random, end of story, case closed?
I
Like,
Well,
think that's a fair statement.
that is a fair statement, although it's not so obvious. I mean, of course, a lot of people might say, "Oh, quantum physics is deal with the smallest thing in the world. Why the hell do we care?" But as our previous episode have shown you, it actually deals with the biggest things in the universe too. It turns out that our universe at some point was quantum mechanical. So the fact that there's an Earth right here where we are, and there's a galaxy to live on, that actually boils down to this quantum randomness. Let's call it that for now. So basically, I think the majority of what we experience in our life is thanks to quantum randomness, right? The amount of ignorance compared to that is probably quite a bit smaller, right? Compared to that universal quantum randomness.
I see. So, is our ignorance and quantum randomness the same thing, or are they different? How would you describe that?
I would say it is different. Like we can look at it operationally, right? Like imagine I flip a coin. I cannot predict how the coin is gonna land, but if I really study it really carefully, put it in vacuum, put the whole coin toss in vacuum, do it with a robotic arms, really study the equation carefully, you can probably predict better than 50-50 what the coin toss is, right? So
Hmm.
that level of unpredictability is down to ignorance. But then if you zoom in really 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 small experimentally, let's say you try to make a coin really small by using subatomic particles, you find that this coin at the quantum level you can actually never predict whether the coin lands heads or tails, no matter how hard you try, right? So that level
Wait.
of randomness is not
Mhm.
due to ignorance.
Wait, wouldn't you? I mean, it is, isn't it? I mean, not to skip ahead, but I mean, you could think of it as a kind of quantum ignorance, right?
I
Yeah, on some level, but you know we can get into this debate of is there some unknown that causes you know this unpredictability. There's this whole debate about you know like a lot of physicists did this, right? I think Bell and company and this famous Bell inequality, and the conclusion is that you you can't just say that because we didn't know and that's why we cannot predict. It's really
Isn't
just
the
that.
conclusion of the Bell's inequality though, is that you can't have zero ignorance? You have to pick a side because it's from the point of view of the observer. So each observer is kind of like implicitly picking a side and ignoring some of the information.
Yeah, well, ignoring information, I think is inevitable in the real world. Like, nothing. You 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 can never like have all the information in the world, right? So
Mhm.
yeah, I guess this yeah
yeah.
this is a bit more complicated. Yeah.
So I guess like let's take a step back. You guys mentioned several words that I'm not sure if our audience is familiar with, like Bell's inequality and just like and then zero ignorance related to Bell's inequality. Like what does this all mean? Like can you break it down? Why is Bell's inequality
Yeah.
important? Like why do we even
Yeah.
mention it?
Yeah. I think the key point here about ignorance is this concept of entanglement. And entanglement sounds like this crazy magical word happens in the quantum realm, but really, entanglement is a fundamentally quantum mechanical concept. It means that there are these hidden correlation that you don't expect, right? So what can happen in the quantum realm is well, okay, let's look at the classical realm, right? Like let's say I flip two coins,
Hmm.
and then you say that, oh, if I flip a coin, that if I flip two coins, both of these coins are totally random due to ignorance. Let's say I cannot predict heads or tails, right? And just because I flip the first coin doesn't mean it can be heads or tails. The same thing applies for the second coin, heads or tails. So we just see this situation in quantum physics. You can cook up a system that's very interesting, that you can have coin one and coin two individually. They are both unpredictable, just like a classical coin. You cannot predict whether one is heads or tails, right? But when you combine them, they're correlated. It means that, let's say, if you can entangle it in one way, say that if the first coin is heads, the second coin will always guarantee heads, right? You can do that, or you can anti-correlate heads. One coin, you can always get tails the other coin. This setup, it's not so obvious. You can't really do that in classical physics unless someone, unless there's like a devious demon to always like, hey, trick the other coin to flip the same way, right? But in classical physics, when you toss two coins, you're doing two toss. It's not like there's some magical demon trying to fix up the second toss, right? But in quantum physics, this could happen. It doesn't matter what order you toss the coin, right? But you can entangle them in such a way that when you toss one coin, you toss another coin. They are perfectly correlated, but yet individually, they look totally random.
So if you
Mm.
just measure one of them, it would look totally random. But you see, it only seems random because you didn't measure the second one yet. You measure the second one, then you would have been able to predict what the
Yeah,
first one was. But you can't do that simultaneously. So there's kind of this fundamental limitation of how much information you can have at a quantum level.
Ah, so what you're saying is entanglement is a kind of quantum-esque correlation, and if two things are perfectly entangled with each other, if I was like at two quantum coins and I flip one and I measure heads, and I knew the other one was entangled, then I also measure heads with the other one. Is that correct?
Yeah, if they're entangled in such a way that
yeah.
one heads
Uh,
implies another heads. Yeah.
I I guess this begs the question, why don't I see this like in the like in my everyday experience? Like where is all this entanglement gone?
Yeah, but I think that's the interesting part, actually. I think it's totally the flip side. It's not that you don't see entanglement. It's more that everything you see actually comes from entanglement. So that's the strange thing.
What you're gonna have to break that down. That's what do you mean everything comes from entanglement? Like, yeah.
Yeah, so if you follow our previous episode, remember that we mentioned that there's this most sacred law in physics is the preservation of quantum information. And the way we frame it is colloquially, we talk this quantum information, you can think of it as the preservation of all the possibilities, right? And the kicker is because in the real world things are unpredictable, and it would seem that if I toss a quantum coin and I get heads, it seems like the possibility of tails are just completely gone, right? So it seems like a loss of information, right? Things are getting, like imagine I got a quantum, I got a quantum coin, and I got heads, right? Then I can't really tell what the quantum coin was originally. I can't tell that. So information is lost. Like maybe the quantum coin was already heads, or maybe the quantum coin could have been tails, right? So there's a loss of information, right? Whenever we see things that are random, there is loss of information, right? But that is contradictory to the fundamental laws of physics. It tells you that information is preserved. This possibility is preserved. So how can we reconcile that? The reconciliation is that we are actually part of this quantum system. We are part of the possibilities. And the way we observe the world is actually through entanglement. We are entangling ourselves with the system we're observing, and that's how we observe the objects, right? So that's why I say the way we see anything is because we are entangling ourselves with it.
Huh. Can you break down, like, maybe experimentally, like a simple experiment, like what does it mean to entangle oneself with the system? Is Tim or Mikey? Go for it. Either one of you.
Well, I don't know. Mikey, you want to give a stab? Take a stab, or I can.
I could give it a stab. I mean, so imagine like you have like the quantum coin, right? And imagine they're entangled in such a way that one being measured heads will always result in the other being tails. If I look at just one of those coins, I actually have to shoot. You can think about it as I have to use a third coin in order to measure one of them. I have to have a third coin and shoot it at one of the coins, and then retrieve that coin and see, this one was tails, so that means that the one that I observed was heads, and then I know that the one that I didn't observe must have been tails as well.
I guess there's this amplification process, right? Like every part of our world, the quantum mechanical bits is small, right? And in order for us to see this quantum coin with heads, like we can't look at it because the quantum system is so small. We can't look at the system directly. So we need some massive apparatus, right, that says, hey, if the quantum coin is heads, maybe it will shoot one electron in some direction, and that electron will shoot other electrons in many other directions. And this cascading effects will ultimately lead to, let's say, a screen that says heads, ding, 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 right? Or if it was tails, some other electron will go shoot into a different direction. And there's this cascading effect, all quantum mechanical. But when you add them up more and more and more, there's lots and lots of particles, and ultimately it will result in something that's macroscopic, right? So I would say these amplification tends to kind of create these bifurcation of different worlds, right? Like you have these small quantum coin heads or tails, but then then you have to follow all the consequences. If there's heads, maybe some dial will happen. It will show up on the screen, and maybe I'll lose $100, and maybe this $100 will cause me to be late on my rent, and maybe I will lose a lot of money, right? And then there's this cascading events that happen, and we are actually part of that event. We're part of that branch of cascading events, right? And so the reason why we see a quantum coin as heads is because we are part of that, right? Like it could have been that we are part of the other branch, but we gotta choose because we're living beings. Like you gotta choose one branch. It cannot be in the middle somewhere. It's either heads or tails because of the way the experimental apparatus is.
I see. I see. So actually, I want to kind of take a step back and make it a bit more concrete. Can we go to an example? Suppose like you're flipping an actual physical coin, like a not a quantum coin, but a classical coin, and you flip it. Like quantum mechanically, can you explain like at least where like the source of quote unquote randomness, like the 50-50, where does that come from?
Yeah, I would say, I guess the quantum randomness in this physical coin would be all the molecules inside the coin, right? And
Yeah.
there's an uncertainty of their location, right? Okay, and
Hmm.
each molecule, they in the beginning they can't decide. Be like, well, where should I be? Should I be slightly to the left, slightly to the right? Because it's all quantum uncertainty. But then, the coin is a rigid coin, right? Basically, so there are
Yeah.
interactions between the different molecules inside the coin. So they are all entangled, right? Their possibilities are all intertwined, right? Like for example, if five molecules from a coin were suddenly to appear in Jupiter or whatever, that coin would break
Mhm.
apart, right? There's consequences for these things, right? So the physics kind of organize itself into distinct possibilities. Is that the coin will rotate in a particular way and flip in a particular way, right? All those possibilities are kind of, coexist, at once. But when you have experimental apparatus, which can just really be air molecules and whatnot, they bifurcate into different possibilities. So you're not going to see like crazy acrobatics from the coin. Like the coin is not going to be like quantum tunnel into itself, twist around, right? It's going to behave like an ordinary coin and land on heads or tails. So I think that's how our observation will come to be.
I think there's a
I,
fundamental limitation when using like a classical coin as an analogy,
mhm.
because the simplest quantum system is kind of difficult to illustrate with a single coin. The simplest system in which you can understand this kind of randomness is kind of like imagine we had this special quantum coin that wasn't just heads or tails. Suppose it had six distinct possibilities: up, down, left, right, forwards, backwards.
Mhm.
Um, that's the simplest system in which you can kind of understand this. So there's six possibilities: up, down, left, right, forwards, backwards. If we have two such coins entangled with each other, if Tim measures the up or down direction, he measures up. If I take the partner coin and make the same up or down measurement, I will definitively measure it to be down. But if Tim measures the up or down direction, he measures it to be up. Suppose I measure the forwards backwards direction. Then,
Mhm.
because Tim measured it to be up, I know that the forwards backwards direction is going to be totally random. There's a 50% chance I'll measure it to be forwards or measure it to be backwards. But that randomness is because of my choice of which axis to measure on. If we had coordinated and if I had measured along the same axis as him, then it would have been totally deterministic, right?
I see. And just for the audience members, like entanglement can also imply the other way around, not just like the same direction. Because you said if Tim measures up, you measure down, but and that's also a concept of fully entangled. It doesn't have to be up for both people, correct?
Yeah. Right.
Yeah.
Yeah. Whether
Okay.
correlated,
Just
fully correlated or fully anti-correlated are the two extremes of how they can be entangled.
I mean, it could be
gotcha.
somewhere in between, right? It doesn't have to be that way. But I would say the general idea is that if we all decide to measure the same thing, we're gonna get consistent answers. And this is because of the theory of entanglement, that says that the probability of Mikey and I disagreeing on the same measurement on a system, that doesn't happen, right? So it's not going to be like I see a coin doing two spins, flip around twice, and Mikey is going to say, oh, no, 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 that's wrong. It flipped around three times. That doesn't happen, right? And we know that it doesn't happen. The world is consistent, right? But if Mikey were to observe another property that's quantum mechanical, like as opposed to how many times the coin flipped, Mikey measures some other very intricate properties. He might get a completely unexpected answer, and that's okay. And that's exactly what we observe in experiments, right? These different measurements, they don't have to kind of be totally commensurate, right? They can be unexpected, unpredictable as well.
I see. I see. That makes sense. So I guess like how does entanglement and randomness like play together kind of coming back? Because it seems like if things are correlated, if I measure one, then the other one isn't as random or like I already know what the other one's going to be. So can we can we like tie these two things together?
It's only certain if you make the right choice of the measurement. In my previous
Mhm.
example, like if you had made an unfortunate choice of measurement, you would have seen something completely random, and
Mhm.
I guess that's entanglement's way of kind of preserving the information, right? Like if Tim measures up uh, and I measure down, then everything's consistent. But if Tim measures up and I measure the forwards backwards direction, then it has to. Yeah. How do I say this?
Yeah, I, 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 I think possibly the way we talk about this, the like the language we use to talk about this system is probably inadequate, right? I think a better way to think about entanglement is kind of like entanglement is a way for you to preserve information. Like imagine if I have two coins that are perfectly correlated. Whenever I flip heads on one coin, I flip heads on the other coin. They might as well be the same coin, right? Like why have two coins? It's just that you can access the coin in a different way, but they might as well be the same coin, right? So
Mhm.
it's telling you that if they are the same coin, or really the same info, if they contain the same information, entanglement is just a way to shift the information from one system to another, right? And this is kind of really clever because like we saw this paradox where quantum physics preserve information and yet it's random. How does it achieve that? It's because the way things appear random is because information from one system slowly gets lost to something else through entanglement. Right? Entanglement is sort of this. It's almost like this. It's like a delivery person, right? It's like delivering a package of information from one system to another, and so on and so forth. Right? So we're constantly losing information out to our environment. Every system is constantly losing information out to the environment, right? And as a result, if we don't consider the environment, it's kind of like we become less predictable. We become more random, at least apparently.
Wait, if you lose information, that means your randomness is going up.
Yeah, basically, it becomes like it's harder and harder to make sense of it, to reconstruct, if you would like, right? And the only way to preserve that information is to not have entanglement. That means you never measure anything. So it's kind of like a conundrum. So that's why like when you measure something, you inevitably mess the system up because the system has to give up some information to you so that you know the system, but then you become part of the system, right? So your information get mixed up with them. So it's like you can never win, right? It's like
I see. So I guess like when we talk about measuring, instead of like thinking of a lab experiment, if I like, let's say I'm looking at this computer right now, am I actually quote unquote measuring this laptop in front of me right now? And it's losing information because I'm looking at least at a classical level.
Well, you're making billions of measurements a second every time you look at the
yeah,
computer screen,
Ah,
right?
how do I
yeah,
not measure things? How
yeah.
do I preserve the
I mean, you
information?
cannot. In order to, if you were to not measure things, you'd be very boring. You'd just be a free particle not interacting with anything. I think like the fact that we exist, we have to measure. We're kind of to live is to kind of get information and also provide information for other things. I mean, that's what makes existence interesting, I think.
So is the meaning of life measurement then in that case?
I mean, I think measurement is a buzzword. I think it's more like yeah. I think it's more just like interaction. Like I think yeah, anytime you entangle yourself with everything else, it's a measurement. And yeah.
So I guess like I want to kind of ask the off the wall question. How would I, if I really wanted to, not entangle myself like with you guys or with this like environment I'm in? How do I do that? Like, how do I escape entanglement? Is there a way to do it?
You just have to make sure that none of the particles that leave your body ever come in contact with our bodies.
Wait, I think you might have to go into a black hole. Maybe that's the only way.
Yeah, I mean,
It's
because gravitrons would entangle us, but you keep it small. You keep the
you keep
entanglement
it
pretty
small.
small.
Like I mean it's inevitable, right? Like you are sending signals to the computer, which is like showing up on my screen, and I'm seeing it. Like the bits, even though most things are classical, like the photons coming from the screen into my eyes, they're entangled, and those are entangled in some ways to your computer and to whatever's your screen. Yeah, we are
Actually, even if you jumped
inextricably.
in a black hole, it wouldn't prevent the entanglement.
Yeah, just maybe future entanglement slightly, because yeah.
I see. I see. All right, then. So basically, what I'm hearing is there's no way to escape entanglement. It's too late.
Yeah, even probably by going to another universe, you probably couldn't escape the entanglement.
Yeah, because I mean, this is kind of because if you subscribe to this sacred law of physics, right? Like
Uh-huh.
because your information it exists in the universe. It just is, right? Like it cannot be destroyed, it cannot be created, it cannot be cloned, it cannot be deleted. So at best, it can be transport. It can be transported from one place to another. So you,
Hmm.
Sahil, like, or maybe you disappear, but at least your information might be transferred into particles around you, and
Hmm.
ultimately, I guess, you know, those particles will interact with something else. I mean, you can't stop it. Like it's
I
hopeless. I
see.
think.
Well, at least I can dream of that. But anyway, so kind of coming back to this in terms of randomness, like it derives itself from entanglement, is what you're saying? Like what we observe, what we call randomness colloquially, comes from entanglement.
Yeah, I guess I just want to dispel this myth, right? In quantum
Mhm.
physics, actually, all the equations in quantum physics are deterministic. There's no randomness in quantum physics, right? There's randomness in measurement. That is true, right? But there's actually
Hmm.
no randomness in the equations of quantum physics, right? Um,
Is, isn't that true for all of math? Like, there's no such thing as like true randomness in math in some
that is
sense.
true. You can debate philosophically to some extent, but it is true. I mean, in classical physics, but you can argue that you know, in let's say in a computer, right? When in a computer, when we compute
Yeah.
things, we always have to there's always some error. You have to round things, and when you do that, there's always this bit of randomness caused by like the erasure of information, right? Because whenever you round something, let's say 1.1 and 1.2 both go to 1,
Hmm.
then you lost information. You lost the information of the little bits, that extra that you
Yeah.
rounded, right? So from that perspective, you can argue that classical computations is random in that regard, because you can never do computation with infinite precision, right?
Yeah.
But that's the difference in quantum physics, right? Quantum physics, if you think of quantum computing, it is operating on infinite precision. There's no rounding whatsoever, and
Hmm.
so combining with the equations have no randomness, meaning that it's exactly like the result of a computation is completely deterministic. You can go forward and backward, right? There's no rounding error whatsoever, at least theoretically. Um, so from that point of view, you can argue that like quantum physics is actually more deterministic, right?
Yeah.
Wait, hang on a sec. Hold on, hold on. I want to slightly challenge that and see what you think. So there's this concept of a wave function, which at least when I learned it in high school was related to a probability distribution, and probability distribution like matches up to what we would use to model randomness. And so you're describing this probability distribution as transforming with time, or the wave function transforming with time. Isn't that kind of a cop out in some sense, or is that not so much?
Well, I don't know what you think, Mikey. I think to me, the wave function, you can think of as a probability, but that's not precise enough, right?
Oh,
It's just telling you the possibilities, right? And then, and if you look at the wave function, let's discretize it a little bit. Let's say the wave function has five parts, right? There's
hmm,
five pieces, and the five pieces can go on and do the different things, right?
yeah,
These five pieces of the wave function can go on different things, and all those different things, they're deterministic. They're completely determined by equations. They're like cellular automaton. You know step by step what they're gonna do, right? They can interact with different parts of the wave function and whatnot. But it's only when we measure. When we measure, then we don't know which one we measure. But I like to think that, you know, if you look at the system as a whole, if you have a eyes view, which we don't, but if we do, you will see every possible measurement. Like Tim might see part one of the wave function, Tim might see part two, part three, part four, part five. All those exist and they're deterministic. But we have to live in one of them because we don't live in multiple worlds simultaneously. So we are
hmm.
stuck. So, you know, that part is we're just stuck in three. Like there's no way around it. You gotta pick one. If it's not three, then maybe it was two, maybe it was one, maybe it was four, right? You have to choose one. So that's where the randomness comes from. At least that's my perspective on it.
Anything you want to add to that, Mikey? Or
I would agree with that. Um,
It's very multi-world esque. I mean, it's a bit of interpretational, but I think that's the most realist point of view.
yeah, man.
all good, man. We can yeah. So we're basically almost at time. I want to leave you guys to say any concluding thoughts if you have any.
Yeah, I don't know, Mikey. You want to go first, Mikey? Thoughts about
It's a little
entanglement?
murky in my head, but all I know for sure is that like this kind of quantum randomness that people describe as being mysterious. Um, there's a way to think about it as being completely a result of the choice of measurement we make, and we can't make a measurement of the same object in two different ways at the same time. And that's kind of the choice that we make with the measurement that creates the randomness from this quantum system that, from as Tim said, the God's eye perspective looks totally deterministic. We kind of select a piece out of it in the way that we choose to measure it, and that's where that quantum randomness comes from. And I think that's a kind of ignorance, right? Because as Tim mentioned, if you could measure it in multiple simultaneous different ways at the same time, then it wouldn't look random to us, but then we wouldn't be humans. We'd be some weird gods of the multiverse.
Well, yeah. I mean, it's really strange that quantum physics has a way of almost like protecting the theory itself, right? Like, in order for us to have this God, if the God was physical, he has to entangle himself or herself with the system, and as a result, also mess up the system. So, so there's no winning condition. I'm sorry, but I think but I think this is a really interesting exercise, right? To think about deeply, what does it mean for us to see something in the world? And I think for a long time in the physics community, we almost have this I would say, what's the phrase? It almost feels like we are a bit we're almost a bit ignorant. We always feel like we're the boss. What we see is what the world is. Like it's like we know everything, but we don't. What we see is just a subset of all the possibilities. I think quantum physics is showing us that. It's keeping us humble in the fact that what we see is not everything, and it's quite likely that the physics behind it, there's way more. And also, the deeper than that, there's also, because of entanglement, um, there are way more information in the world than we are privy to. Like, we can only observe so little. There's so much more. There's all these strange correlations that when you go into the lab, you see it, but of course we're completely ignorant of in the real world. And these are could be informations about the other possibilities that we're not seeing, right?
Mhm.
And I think it's interesting to be mindful of that, right? That ultimately we are somehow related to all these cosmic correlations, you
Oh, and then one final question I want to ask you, just to like, you know, put the nail in the piece of wood, or I don't want to say coffin to be morbid, but
know.
um, so if we didn't have entanglement, suppose it did not exist, what would the universe be like? Like, why is it so important for our everyday life, like the way we exist today?
I think it's what you mentioned at the beginning. Like, if there was no entanglement, then nothing would be correlated with anything else, and then it would just be pure chaos. I mean, everything would
That
be independent of everything. There would be no relationships between any two objects. Yeah.
Yeah, I think that's true. Yeah, then then without, yeah. So I think that there are two possibilities, right? Like without entanglement, you can insist that information is preserved or information is not preserved, right? If information is preserved, then the universe will be very boring. Basically, every single particle will have to become super narcissistic. They're just by themselves. They're just completely uninteracting, uninterested in anything. It would be a very sad universe because nothing will ever happen, right? Or if you subscribe to the fact that maybe information is not preserved, that it's just like a computer with rounding errors. If you allow, you know, when things happen, there could always be some rounding error, whatever, right? Then, like Mikey said, it's just going to be chaos, right? Eventually, these just like these errors just totally, what's the physics behind these errors? Either it's completely unspecified or just some like overwhelming noise. Like then it also feels strange, right? It almost feels like it's purposeless. Almost feels like, right? They're just some completely like non-traceable things in the universe, and that feels even stranger, I would say. Um, yeah,
Yeah, I would agree with that. I'm glad that there's entanglement. Otherwise, we wouldn't be here talking about entanglement if it wasn't
exactly.
there for more than just the uh, subject matter itself not existing. Yeah. Well, with that, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thanks for joining.
Bye.
Bye.
Bye.